Good evening, everyone. Welcome to 10th live session for the course Usability Engineering. My name is Neelarnab Dutta, and in this particular course, I'll be discussing about week 10 lecture videos. And this will be a doubt clearing session, so please be interactive in that class. So let's start with some recap from last class. So in the last class, I have discussed about various ideation techniques, and I have discussed about the differences between creativity, innovation, and ideation. So creativity, as I described, is basically the ability to come up with ideas, Okay, ideation is the process of ideating, the process of coming with solutions. That is what is we defined as ideation. And innovation is basically those outcomes, those solutions which are novel, useful, and also non-obvious for someone skilled in that particular art. And first, you have invention, and when you make an invention more useful and more implementable for the society, for people, what we have is innovation. So that's what we described in the last class. Then I described that the creativity, although it's a natural process, this can be enhanced by using certain techniques, and these techniques are very common when we talked about concept designing, doing ideation during a design process. So I have discussed about several ideation techniques like brainstorming, brain dumping, mind mapping, etc., etc. Then I discussed in detail two of such techniques. One was reframing matrix, which basically consider a business problem and try to see the problem from different occupational viewpoints. For example, I have described a 4-point perspective where you can see a business problem as from product planning perspective, then potential perspective, and then people perspective. Okay, then you will get different insights and different viewpoints, and these viewpoints will help you trigger more ideas from different perspectives. So you end up having ideas which are diverse in nature. So instead of ideating from single viewpoint, which is often the engineering or design viewpoint of solving a problem, you will have multiple viewpoints and you will probably ideating from those perspectives. Then we discussed about scamper, which is basically a technique, and in that particular technique you use a base concept, a base model. Probably it can be something which is already available, or it can be something, a basic concepts that you have come up with, and then you try to use these keywords: substitute, combine, adapt, modify, put to another use, eliminate, and rearrange. So these individual keywords will trigger to make certain changes to the existing base model. For example, substitute. You will try to substitute something, whether it's a substitution of material, substitution of user profile, substitution of the process, or the arrangement of components. Again, combination can be like combining different aspects to make it simpler. Adaptation can be adapting something from another sources and then try to combine and adapt those into your product. Okay, so like that we can use these keywords and ask various questions how we can use this particular keyword while ideating, while generating ideas, okay, in terms of these perspectives. So these are more like different perspective which were actionable. So these are actionable perspectives. Then I discussed about different kind of thinking, okay, which are necessary for ideation. So we discuss about divergent thinking, which is basically thinking from different perspective. So instead of going vertically down, deep down for one concept or idea, you are trying to generate multiple ideas. This is what is divergent thinking. Okay, so then we discuss about how we can achieve divergent thinking. Okay, then we discuss about what is convergent thinking. That means once you have a lot of ideas, you try to analyze those from certain matrices, certain filters, and then try to group them and see which of them are actually useful for you. So that is again convergent thinking. Then once you have selected few concepts, then you actually try to go much detail, which is linear thinking, okay, versus lateral thinking. So linear thinking and lateral thinking basically not same as divergent convergent. Linear thinking is like, although it means vertical thinking, but it is not convergent. So convergent and divergent means spreading and converging. Okay, linear means going in one direction, lateral means going in parallel directions. Okay, so while doing divergent thinking, you can do lateral thinking. Again, while doing convergent thinking, you can actually go for lateral thinking. Similarly, during lateral thinking also, linear thinking also, you can go for convergent thinking. So these uh, different kind of thinkings can be used to get to increase the quantity as well as quality of your ideas. Okay, so once we have generated a couple of, a bunch of ideas, the next step is to actually select few of them and then start detailing out and try to see how we can achieve, okay, a particular need that the user is looking for or stakeholder is looking for. Okay, because after defining those individual interactions, the small requirements, only then we can analyze a concept, whether a concept is viable, feasible, or is useful or not. Okay, so what we deal with in that particular process is what we call as designing for micro interaction. Okay, now micro interactions are basically the functional interactive details about a product. Okay, that means from functional point of view, we do functional decomposition. So when we have an idea, for example, here is a product, okay, which is a idea at this stage. Okay, and the ideation technique here use is sketching or sketch storming, you can say sketch storming, and you try to define how you can solve a particular user requirement using these images and explanations. Okay, okay, so after doing this, the information here is missing is how this will work. For example, this is a small interface, and what's actually there in that particular interface needs to be detailed out when we actually going for further concept development. So this detailing process involve designing for these micro interactions. Okay, that means now we are trying to define how these interfaces look like and how they perform from functional perspective as well as from interaction perspective. Okay, so functional requirement is what is required for a particular concept to evolve, for a particular concept to perform, and interactive requirements are how a user can interact, can actually use that particular device. So what will be the mode of communication between the device, okay, device, this is your user. So what will be your, how you will communicate. Okay, so this is what you design when you design for interaction. Okay, so these small design things, what we call as designing micro interactions, are actually small sub level design activities. When we combine them, then only we achieve the bigger objective. That means the goal of micro interaction is always need driven. Okay, so we have a particular, for example, task of running this particular device probably. So starting a device, for example, start the device can be a micro interaction. It's a need, okay, a overall goal. Now for starting, now you need to go into detail what functional requirements I'll be looking for. So functional requirements means I will be able to start a motor. For example, a DC motor is there inside this particular device. So functional requirements mean there needs to be a DC motor, and the DC motor needs to be connected with some sort of button. Okay, and then we'll discuss about how we'll be providing the interaction. So interaction will be a push action. Okay, so push action, and then you will get some sort of feedback. For example, you got a beep sound. Okay, beep sound. So all these aspects which are functional in nature and interaction in nature, they combine and they serve certain goal. Okay, now these small goal can be a sub goal for your overall product design. Okay, so likewise, when you actually do multiple of such sub goals, okay, probably you will fulfilling the overall requirement of the concept. So this is probably the concept, and when you break down the concept from functional perspective or interaction perspective, then you will have individual goals, and then you try to design those micro interactions. Okay, so that is what is micro interactions. Okay, now the importance of designing like that is that this way of designing a concept or detailing a concept actually help to make a solution which is more engaging. Okay, which is more engaging to the user, and you try to come up with functionalities as well as interactions which are very natural to that particular user. So that's why you go into detail and you try to design around, you try to detail out each of these small interactions and small functional details you try to achieve. Now micro interactions also give you experience. So a bad interaction design or functional design can give you bad experience. Similarly, a good design will provide a good experience. So detailing out concepts by designing micro interactions is vital so that you provide a good experience to the user. Okay, now we need to understand how to design for micro interactions. Okay, now each of these micro interactions, so when you call as a micro interaction, that means now we are talking about small activity which involve, so this is a micro interactions, then it involves functional, there's a functional goal, and there is a interaction goal. Okay, now there is a structure of how you perform micro interactions. So the structure of micro interaction include a trigger. Okay, so there is a concept of trigger. That means a trigger is something which initiate a micro interactions. Okay, so trigger is something which initiate a micro interactions. For example, if for a particular device, when you press a button, that machine will start. That means that's a trigger. Then rules. Now rules are the set of logics how the particular device will run, or how it, what it will provide to the user. Okay, so this is basically the algorithm part of a system. When we talk about a electronic device, if it is a web interface, then it is the logics or the architecture. Again, there are software algorithms involved in web design. So those are all rules, and rules try to define how user will interact, what will be the outcome, what will be the feedback, So all sort of things are defined by rules. Okay, so rules is the second component when we are designing micro interactions. Then feedback. Feedback are necessary because when user provides certain triggers, he or she needs to understand the state of the system. Otherwise, he may keep on triggering, providing triggers again and again. So if you will not give any feedback of change of state or change of display, probably the user will not understand whether the system accepted his input or not. Okay, that's why feedback is important. Okay, feedback is important. Now, loops and modes are meta rules. That means meta rules means the rules that describe how other rules should use. Okay. Now, loop is generally used when we try to use time or try to define time for a particular activity. For example, when we want to run a particular task for 3 seconds, for example, you want to make a beep sound for 3 seconds, you probably switch on a buzzer for 3 seconds. That means that particular action of triggering that buzzer will run in a loop for 3 seconds. So that is what is a loop. Okay. So loops are useful when in a particular logic or in a rule you try to be inside a particular functionality for certain amount of time. So then you provide some loop, and the particular software or algorithm try to provide that particular features for a particular uh, time interval. Okay. Now modes are basically of different types, but most commonly modes are used when you have different modularity within your system, whether you call it a software system or it's a hardware. When you want to have different modes, and you do not want interaction between these two modes, mode 1, mode 2, then we use the concept of mode means, for example, in a software system or in a device you can have setting mode. So when you are entering a setting mode, you will be provided with different set of functionalities as well as interactions, and at that time probably you will not be have access to the system running the input output facilities. Okay. Similarly, when you are actually in a running mode, system operation mode, probably at that time you will not be able to access the setting. Okay. So like that, when you actually try to distinguish different set of functional elements, functional elements 1, then functional elements 2. So these are set 1, set 2, plus interaction set 1 plus interaction set 2. So when you want to when logically you want to establish two different set of functional as well as interactive elements, then you use the concept of mode, where you functionally or you logically make distinguishable meta rules to operate a particular system for certain set of rules. So you have set rules here 1, then you have rules here, rules 2. So rule set 2, rule set 3. So meta rules basically describes how other rules should be used. Okay, so you have a lot of rules, probably 100 rules. So 20 rules you try to group them using one mode. Another 30 rules you try to group them into another set of modes. Okay. Okay, so these are the four basic elements in the structure of the micro interactions. So let me give you an example from a case study. So then these concepts will be clear. Okay. So this is a project where basically I have come up with a concept for a wound healing solution. Okay. So this is at the ideation stage, And here I try to define the system. Okay, how the system will be look like, how it will be going to operate, what will be the functional uh, benefits or application of this particular device, and how the product or device will be used to a human subject. So this is a wound healing device. That means this helps in wound healing. So the device is this one, and it will be connected with a dressing which has silicone tube, and this dressing will be actually connected, or it will be placed on a human body, so that the wound underneath wound get healed faster. Okay. Now this particular concept now at this stage at the sketch level is at a very basic level, where one cannot understand whether one need to select this particular concept or not, because like that you may have multiple such concepts at this particular level of detail. So you need to detail these things out, okay, for further analysis. Okay, so based on this particular idea, what I have generated is a list of requirements which are required for user interaction or user experience. Okay, so this particular device have these requirements: therapy selection, configuration, application. That means this device should be able to select a particular therapy. That means the concept of mode come here. Okay, and when we talk about a mode, that means when you switch between two different mode, you want to run the system within that particular mode for some time. That means loop. The concept of loop again comes. That's why modes and loops are often called together, because they are dependent on each other. Okay. Now runtime status monitoring. So runtime status monitoring means whatever is happening to the system, the information should be visible to the patient or to the doctor. That means we are talking here about the feedback. Okay. Feedback. Okay, then again emergency and fault recognition. These are again, in case system face any issues, it should actually detect that particular emergency scenario, and then provide some feedback. That means these are system level trigger that the particular system should understand. Again, to design this whole system, we will be requiring rules. Okay, so let's see how we achieve this. So first, based on these requirements, which are actually part of user requirements. Okay, so these are basically the consolidated information from user study. Okay, so some of the requirements which were later converted into functional specifications. Okay, so once we have functional specification, now the ideas which are initially very abstract in nature, they try to those are getting more clarified, and they are started becoming more concrete in nature. So as a functional specification, what we want to have actually a therapy mode selection. Now we are trying to define the micro interactions. Now interaction in terms of functional elements as well as interactive elements. Okay. So when I say therapy mode selection, that means there should be a functional requirement that you need to provide a button or something for therapy mode selection, so that one can change the mode. Okay, then selecting and setting parameters. This is again we are talking about parameters. That means those are functional requirements. You may require to set certain values while starting this particular device. So that is what is functional requirements, and there should be some way, okay, how you select a particular parameter, and then you provide a certain value to it. Okay, so this is again from the perspective of functional requirement as well as interaction requirements. So like that, for every content, every requirement which is initially provided, which are for sorry not provided, which were consolidated from user research data, now we are trying to define them from the perspective of micro interactions. So we are trying to define these functional specifications which involve both the functional as well as interactive aspects of the specification. So starting, pausing and stopping therapy. Okay, so for this first requirement, we need these three specifications. Similarly, runtime status monitoring of therapy information. That means when you want to actually have information on the runtime information about the system. So first thing is like as a specification, you need to the system should provide high priority informations, okay, to you. So real time monitoring. So you should be able to real time monitor. That means here we are talking about the system. If system is running and it's doing some activity, and if some high priority information come into picture, system should actually stop particular running condition and still uh, it should be able to show you those information. For example, if you're operating the system and for a critical patient, probably there are certain scenario. For example, there may be leakage, there may be some accidental breakdown, and those are like uh, high priority decisions that the system should be able to make, and it should inform as a feedback to the user. Okay, then therapy duration. So therapy duration, from how long this particular mode is running, so all those details needs to be provided. So this is what we need to achieve as a part of this sort of content requirement. So likewise, actually this is a small list I am showing here, but there are a long list of various functional specification those are provided for like these user requirements. Now the next task was to actually convert these functional specification into interaction ideas. See, a micro interaction is now starts developing. Micro interaction. You are talking about functional specification, then we are talking about interaction ideas. Okay, so this is what we do generally when we actually try to come up with a more concrete solution, more concrete idea, which we call as a concept. So you have an idea. Now these ideas are converted into concept. Now concept involve detailing out these micro interactions. Okay, so now therapy mode selection means one tactile mode button to switch different therapies. See, these are again ideations. There are maybe different ways how therapy mode can be selected or changed, but in this for this particular concept, I have freezed one particular option which is initially thought, because here there are 3 4 buttons. So initially this was what thought. So I am now trying to define this, that there is one particular button which is useful for changing the mode. Okay. Then selecting and setting parameters. That means you need to have previous, next, plus, minus, etc. buttons. Okay, now this is not exactly the interface. Okay, so you can have a mode button here, you can have plus and minus, then you can have previous and next. Okay, so this is the mode button for the therapy mode selection. Then for selecting and setting parameters, you need to provide 4 buttons, because you need to move uh, to different parameters first. Okay, so when you do previous, probably it will go to a previous parameter, then when you go to next, probably it will move to a next parameter, then when you press plus and minus, probably it will increase or decrease that particular value for that particular parameter. So that's why you need 4 buttons. So here you need 1 button. So like that, actually we plan for how will we provide the trigger. Okay, now I'm discussing about the trigger perspective. So triggers are the front end where the user actually interact with a interface. So user interact with a interface with set of triggers. Okay, so the triggers can be of two types. It can be like manual triggers where the user involve or press a button, or it can be system level triggers where the system detect certain event, okay, or interrupt, and then it actually do certain action. Okay, so now to perform this particular therapy, when it's choose a particular therapy, there should be some set of logic, right? It will do that, it will do that. So the algorithm part of it actually is what is the rules. Feedback, as I told you, whatever runtime status information that needs to be visible on the interface. Okay, that is the feedback. Loops and modes, when you select a particular mode, the system should run in that particular mode. So like that, when you design a interface, you need to consider these four aspects of micro interaction. Okay, so let's discuss this in detail. Okay, so first thing is designing of triggers. Okay, now as I discussed before, triggers are user initiated. Okay, so this can be user initiated and it's not always required. So so triggers can be user initiated, and this provide the user a way to do something. Okay, so these buttons will actually allow the user to do something. Like for example, if pressing, it will start. If you press this low button, probably it will decrease some pressure. If you put it mid, probably it will, or these are like fixed settings where low means this is the value of the particular parameter, mid means this is the particular value, high means this is the particular value. That means you are fixing certain parameter value, and for that you are providing three buttons. So trigger allow you to select a particular functionality using a particular interaction feature. Okay, so these are examples of user initiated interactions. Okay, now I told you like micro interactions begin with an understanding of user requirements. That means these were developed, these contain requirements, as I told you, they are actually consulted information of user requirements, and then those were converted into functional specification plus interaction ideas. But indirectly, these are actually the implication of user requirement. Okay, now as I told you, triggers need not be user initiated always. It can be system initiated also. That means, for example, the system detect a event where there are leakages while this dressing is implemented on a human body. Probably there are some leakage happens. Okay, or something happens which are clinically dangerous. Now the system, the therapy should stop, otherwise this particular condition may became worse. So you need to stop that particular therapy, and for that actually you need to inform the person who is actually in response, who is responsible a particular task. So you need to provide him some trigger, some feedback information. Okay, so to provide that feedback information, the system should first detect that event and then trigger that feedback, no feedback, particular feedback mechanism. It can be a long beep sound or it can be alarm. Okay, so those triggers are generally system initiated triggers. Okay, another example can be, if you talk about your mailboxes, when you talked about the softwares. So whenever a mail comes which the system detects as a spam mail, it automatically get into the spam folder. So you as a person does not actually move that. The system itself detect. So these are smart algorithms, machine learning algorithms, which can detect whether a particular mail is spam or not, and it can actually trigger that particular action where this particular mail is then deviated from the inbox and then sent to that particular spam folder. So this is an example of how spam mail can be sent to a spam mailbox using system initiated triggers. Now trigger initiates same action every time. Now this is important. Okay, normally when we design a particular micro interactions, we try to fix our action against a particular trigger. Okay, because otherwise it will be confusing for the user and it will affect his learnability. For example, if you press this start button, uh, see, start button is a better example, but if you see high, if you press this high, the system should always go to a high setting. Okay, that means the user should understand easily that this particular button is used for setting the parameters at a higher level. Similarly, when you press low, it is actually setting the parameter as a low level. Okay, now here the kind of interaction like single action, like so for every trigger you will be achieving one particular action and which is desired actually to have learnability. But here, because of space limitation or because of some constraints, I have put one particular button for two actions. So it is push to on, push to stop. So for example, this is also useful because this is limited by two action, one is start and one is stop. But to implement double two actions for a single button, you need to provide some sort of feedback which actually a user can recognize. Okay, so those design decisions, those micro design more micro interactions you need to think about, and those are actually the feedbacks. Okay, for example, when it is a start mode, you will see that this particular value will be changing. That means the person will automatically see based on these visual feedback that okay, the system is in a start condition. That means after pressing a second push, okay, after providing a second push, the system will stop. Then visually these elements will stop because you have a running time status here and then you have a value here which is always changing. So visual feedbacks are actually necessary when actually you want to implement more than one action corresponding to a trigger option. Okay, so this is what. Otherwise, you always considered one particular action and same action every time when you trigger a particular button. Okay, because this will help system. It will make the system easy to learn and easy to use for novice user. Okay, so here are some information that you need to consider for designing triggers. So you need to consider bringing the information forward. Okay, so it should not be like users should understand the status of the system even before he execute a particular trigger. That means if the user actually, why user will think whether he has to push the start or stop, because the user will see values are changing here. That means the machine is in running condition and already for example half an hour is elapsed. Okay, that means now it's time, so those decisions user can make, and now based on those feedback he will press this particular button. So these sort of data about system information needs to be provided upfront. Okay, similarly, if these are not moving, so there can be two causes. One, either system got hang because of some fault, or system is not in a running condition. Okay, now generally when system is not in a running condition, you will have a black screen. It will not be a hang screen. So that's why you need to make sure when you're designing a particular interface, you need to make sure that when you are in a stop mode, it's better if you can intentionally make the screen black. There should not be any residual information because then it will be confused with a system which is in a hang state. Now a clear indication of these sort of data upfront will help the user to make certain decisions and make interactions correctly. Okay. So another example can be like in a button. So when you actually move your cursor over a button, when you actually roll over, you will see a change in the color or in the gradient. Okay, see now it's a gray gradient when you actually roll over your cursor, but this is before you press the button. Okay, now when you actually try to press the button, it will actually change it to blue. Now this information will be stored, the system will be blue, and if you see a blue button, then you will recognize that the button already got pressed. Similarly, if a button is not blue, it's gray. If it is white, that means it's not yet active. The state is not yet active, that means button has not been pressed yet. Okay. Similarly, when we actually move, it will give an indication that the button, the cursor is actually within the range where actually you can actually click the mouse. Now if you put the cursor here, probably that's not an ideal position where you will click that particular button. Sometimes people make buttons like that, but they will make it only this particular letter active. So while your cursor is actually within that particular box, still it is not changing. Okay, so if you design such interactions, so people will get confused. People will actually try to click that particular button while not above that particular text, and he will not get any results. So designing such elements need to consider all those uh, details about trigger, how to design the trigger. So you need to provide the data upfront. That means you need to inform the user about the state of that particular system when actually you are moving your cursor. Okay, so designing trigger needs that. Some examples are like for a single action, a single button can be used. Okay, for example, if you want to just increase the volume, or if you want to fast forward, okay, so a button or a simple gesture is good for choice. Similarly, if your action has two states, for example on off, so this is like an on off button, start and stop. So what you can have is a toggle switch. So this button is something like a toggle switch. Now a physical toggle switch is something like a electrical switch which actually have two states. You have the off state and then on state, and actually visually you can see the difference. It became like that at the on state, and during the off state it is like that. So this is off, this is on. But for digital buttons, or if it's a physical button, push button, when where you do not have such change in the shape, probably you can provide information on the display about that particular feedback, or you can actually lit, you can provide some sort of backlit where it will show that now the system is in running condition. So those level of detailing you need to accomplish when you are designing triggers for actions with several defined states. So you can use a dial. So dial is basically the one like a knob where you have different states. Think it like a knob for a oven where you have different temperature settings like that, and when you actually rotate, you can actually set different temperature. Action along a continuum can be defined with a slide or a dial. So if it is like a volume, increase in volume, so you can actually use a dial or you can use a slide. Okay. Where there is no no fixed setting interval, like a like for example this temperature setting, there is no fixed marking for volume control required actually, because you can increase just by rotating. Nowadays cars have dials which do not have any end point. It will keep on rotating and you can reverse, and it will keep on rotating both clockwise and anti-clockwise. Because the idea here is not to give a exact scale where moving this particular level will increase the volume that much, because you do not have that sense of sound, you do not have that distance, like how much you will rotate and how much the sound will increase. That's the reason why it is not important that you will be provided with a dial where there are the volume settings are defined. Okay. So you have dials where no such markings or information provided, but when you rotate it clockwise it will increase your volume, when you rotate it anti-clockwise it will reduce your volume. Okay. So for such continuum action or functional requirements, you can use a dial or a slider. Now you need to consider one thing, like when you are designing a trigger, okay, you do not break the visual affordance. That means when a button is designed, the user have the tendency to feel that this button is pressable. Okay, but if you make a button but you say, oh, this is not a button, this is something like a rotating knob, then that means you broke the visual affordance, because a knob is always like this and a button can be rectangular or a push button. Okay, but if even a push button is circular in nature, you provide some sort of indicator so that people understand that this is rotatable or this is push button. For example, for push button you provide this kind of graphics. Okay, so do not confuse user with different trigger visual identity, where the user get confused and it will actually hamper his interactions. You also need to consider how frequently a particular trigger is actually used. For example, if a trigger is used very frequently, probably you need to change the mode of that particular trigger. For example, a frequent use of a button may actually impact the longevity of that particular, the lifespan of that particular button. Okay, if a trigger is used very frequently, it is better if you provide something else for that particular action. Okay. For example, if you are thinking of changing the settings, okay, for example, one will choose low mid high frequently, probably it is better if you can provide a dial instead of three buttons. So like that you need to decide your trigger design also based on the frequency of its use. Okay, next is rules. Okay, now rules are as defined are the heart of any micro interactions. Basically it's like when you are actually playing some game, there are certain rules which actually enable you to win or lose. Okay, so rules are like that. For any system design there are rules actually how a user will interact. Okay, how, what are the, is it a sequential or is it parallel action, but these rules are defined like how you will interact and how you will the machine or the system will perform. So this is what rule defines. Now rules determine how the micro interaction respond to the trigger being activated. For example, when you start press this button, what is the outcome? The outcome is it will start the system, right? Start the system means what? It will start a motor. Okay, now based on what? Based on these parameters. Now you said that I will be running this machine at a low, for example, pressure level. So how the system will detect low pressure? That means there are some sort of sensors available, and that sensors, there's some central processor CPU which actually will monitor that sensor value, and then it will, based on that particular sensor value, it will drive this motor. Okay, so this start, the logic behind, the rules behind this particular trigger start and stop is this, that a sensor value will be first detected, and then system will run a motor. And every time you have a change in the sensor value, the speed of the motor will be also changing. That means the CPU will maintain a balance between these two. Okay, so this will be a loop. Again, what controls the user has over a micro interaction in the process. Okay, so when you are designing the rules, you need to also see what controls you have provided to the user. So now when you have set the rules for the start button, now you have also provided the controls for changing the value at which this particular motor will be running. So depending upon the pressure value, the motor will run at a different value. Okay, so these are the user controls that you have provided. Now user can choose any one of these three parameters, and then he can actually select the state of the running condition. Okay, so that's what it is told here. The sequence in which the action take place and the timing thereof. As I told you, the entire interaction, how various triggers will be made, how what feedback will be provided, how the system will run, what it will be showing to the user, what will be the feedback, how what will be the modes, what will be various looping conditions. All those will be defined by rules. Okay, you also consider what data need to be considered. For example, here sensor value needs to be considered by CPU, but CPU will then give input as a electrical voltage. So there are different data types which that logic needs to handle. Okay, now rules also determine the configuration and parameters of any algorithm. Now let's say the algorithm of this particular machine. Okay, so same thing I just discussed. So you have a start button. When you start, now what will happen, this start button actually trigger a CPU. Now the CPU's task is actually to run a motor, a DC motor. Okay, but it will not run it at a very high speed. It will have a feedback from a sensor. The sensor take information from the real world, which is from the dressing. Okay, and then it will tell the CPU that okay, this is the pressure value. See, pressure value is now in mmHg. Now this is a parameter. Pressure value is a parameter. P value, unit is mmHg. Now running the motor, you need to change the voltage or current. The values are voltage and current is ampere. Okay, milliamps you can see. Now see, these are again different parameters. Now based on the sensor value, the CPU will the system will run. So this is now going to be in a loop. Okay, so once it is done, it will stop here. So this is a small simple logics of a one particular interaction, micro interaction, which is the start and stop button. So this is this for this particular button, logic for this particular button. So this is the rules will determine the configuration and parameters, okay, of this particular algorithm. So this is one algorithm. What feedback is delivered? That means what sort of sensor value we are actually getting. Again, the sensor values also needs to be determined. Like for example, CPU can also provide details to the user display. That means system is running internally with the feedback, and some of those information occasionally the system is also showing to the user. So this is for user. So user feedback versus system level feedback. Okay, what mode of micro interaction is in? So system is now at a start mode. If it is stop mode, then this will not run. Okay, so there are two modes here. It's a toggle switch, start mode and stop mode. If the micro interaction repeats, how often? Okay, now rules also determine how often specific interactions actually repeats. For example, reading the sensor value. Okay, at what frequency the CPU will actually read the sensor value. For example, for this particular system, if CPU actually needs to control the particular motor running condition, it needs to actually provide the control after some time interval, right? So the frequency at which it can read the sensor, probably if you say every 3 seconds, the CPU is actually reading the sensor value, and then at the fourth, at every fourth second, it is sending the information to the DC motor that now you run at this particular voltage or current. Okay, so a system, a rules also determine how you will be repeating a particular action or a particular loop in a algorithm. What happens when the micro interaction ends? What happens means this particular start activity, when it ends, what will happen? Will the system stops or it will move to another state? So all those things actually will be provided to you. Probably there will be a change in the display also, that now the system has finished the particular therapy or it will enter to a different setting. Okay, so those can be determined when you are designing rules. Screens and states. Okay, now when designing rules, now some of the consideration you need to make is like, rules needs to implement it by keeping in mind the state of the system as well as what is being displayed. Okay, so an object that user can interact can have three states. Okay, it can be a default state, which is like not doing anything. So when it is not running, probably you should not show any information, it should be a black screen, or maybe some introductory information about what the system can do. Now when it is in a active state, probably it will be showing the particular system level information, and it will not show all the information. It will only show the information that is actually necessary for the user to know. It will not provide you the information about the value of the motor or sensor, the current going into the motor. All those information are unnecessary. You need to know that system is running at this particular pressure level and it is running for this time period. Updated state, that means whenever the system is changing its value internally, for example it is changing its pressure, the system should be able to provide those updated value as a feedback to the user. Okay, so within the within the rules you need to provide information, or you need to provide logics, so that system display the state of the system and it changes its screens. Okay, also you need to define the constraint within which actually you will be designing the rules. Okay, for example, you have to fix your input output methods probably. For example, here input output methods are button press, output is displaying by LCD. LCD, these are buttons. Okay, now these are one option. You could have a audio input and a visual output. You could have only audio and audio output, audio input as well as audio output. You could have only touch based input as well as visual output. So kind of input and outputs also needs to be decided when actually you are designing rules for the system. Now range of input. Okay, so if you are making a system which have the values more than these settings, probably you need to add more buttons, or you probably need to change the particular trigger. And when you are changing the particular trigger, that means now your input, the button changes, and the way the in logics how you actually you are reading that input value will also change, because now these are not the strict values which are actually sent by different buttons. Instead of that, if you are having a different range, and for that you need to use something like a knob, probably you need to use some different logic how you will determine a particular state of value. For example, whether the particular knob is at 50 or 60, how the system will know. Okay, so there should be some way how the system will detect that change in position. Okay, because here what happened when you have three different buttons, minus 80, minus 120 and minus 200, you actually have a fixed value. When you press this, you will having a 80. When you have press this, you have a minus 120. But when you use a knob, it's very difficult to detect at what level it is. So you need to use some rotatory encoder, then you should have some analog digital converter, then probably your system, the CPU will detect how, at what position this particular knob is in. Okay, what kind of data is available? Okay, like same like here you have mmHg. Okay, now instead of pressure sensing, if you provide something else, for example, if you now want to provide audio sensor is signal. So instead of a button, you now have a active sensor like a mic. Now based on the mic, now you want to determine the pressure level. Okay, so based on the data, okay, how you can collect those data and what how you can use that data, your logic, that the algorithmic logic, the flow will change actually. So those you need to consider, the constraints you need to consider actually when you are actually designing rules. The third aspect of designing rules is preventing errors. You design, you pre-plan the logics is because you want to make sure you are choosing a most appropriate way how the system should function. That means your logic should be free from any errors. There should not be deadlocks. There should not be, um, you know, areas where the system can actually go into run. It's called uh, what is called it's called in the embedded system, what we call as uh, running condition, something like that. Running condition probably, I forgot that actually now, or probably it is, so basically system enters into a particular state from which it actually cannot recover. So that particular state is something called run, something like that similar. So which is a state where, because you jump within the logics from interrupt to another interrupt, and actually you lost the track where actually your program was before. So because of that, you actually enter into that particular state where actually there's no way you can actually return back to that original program state. So you are actually now in that particular system runtime or something called uh, some that particular state where actually the system will hang. So you need to prevent actually all such errors. So errors which actually create faults, which actually uh, creates hamper the safety of the user. You need to avoid those. Okay, you should also avoid deadlocks. Okay, next is feedback. So feedbacks are important, as I told you, because without feedback, the user will not know whether a button has been pressed or not. So the main importance of feedback is like whenever a button is pressed, the user should know the status of the system, whether the button got pressed or not. Even prior to button pressed also, this system should provide you the information about a particular trigger state, whether the particular trigger has been already pressed or not. Okay, so depending upon the visibility of a particular system, you should be able to know whether the system is in running condition or it is in particular mode or not. Okay, then after, you know, after detecting that precondition of that of a particular state of a system, you should actually when the user will trigger a particular input output modularity, you should also provide feedback about that action which the user has performed. So it can be like a beep sound, it can be some sort of vibration, okay, like that. Actually, you can provide feedback. Now you need to think one thing, like you should not overburden the user with feedback, because sometimes what happen, like when you actually overdo with feedbacks, it will increase cognitive overload. Okay, it will actually be information overload, which will actually create problems for the user to actually carry out his activity. For example, when you are dealing with very small interface where you do not have much space to provide information, but if you want to provide feedback here, probably that will make the interface very cluttered and this person will get confused. You will probably not able to detect the feedback itself. Now, best feedback is never arbitrary. That means the arbitrary feedback makes it harder to connect for people. It should not be something else. It should be well defined and easy to understand. For example, you should not mix the sound of an emergency with the sound of simply starting a therapy. So probably if you think about distinguishing the sound of emergency versus starting a starting a therapy, probably you need to create that difference. Okay, so choice of feedback is also necessary. You should not choose something arbitrary in nature. Now feedback should convey the most with the least changes. For example, when this system is running, so instead of disclosing a lot of information, probably only changing this particular um, blue strip, okay, probably will give the indication that system is now running. Okay. Similarly, if battery is low, probably only changing the color, that now battery is in red color, will probably give you the information. So you need to actually provide the minimum action, you need to provide the minimum visual information so that it is easy for its recognition. You do not have to give text messages that your battery is low, please recharge. So it's not like that. You need to provide minimum information and you need to achieve the most out of feedback. And often overlooked features, okay, can be used for providing feedback. For example, in a particular space, when you are considering space, you have some spaces which are often overlooked. For example, the extreme edges of the interface can be used for feedback, providing feedback. Okay, that's where actually you have the least important elements, and this central portion actually covers the most important elements. So probably you can use those overlooked portions to provide feedback for that particular system. Okay, so feedback can be of three types. It can be visual, audio, as well as haptic. So visual is like display. Audio can be like a beep sound which will be generated. It can be like a manual. It can be triggered from a manual trigger, or it can be a system level trigger where system will generate audio or beeps, a long beep sound in case of emergency. Okay. Haptic can be something like a vibration whenever a mobile phone is in your pocket and someone's call. Now system triggers. Now that's a system trigger and you will get a vibration. Okay, so there are four rules for designing feedback. One is contextual change. You need to ask yourself, does the feedback changed based on the known context? For instance, if it is night, does the volume increase or decrease? So now two things you need to consider here. One is you provide feedback when there is a contextual changes, whether there's a mode change or button triggered or something. Like whenever there is a change in state or context, then you provide triggers. Second thing is like depending upon the requirement, the nature of the feedback may change. For example, in the night when you have a phone call, probably the display should choose different color options to show certain feedback. Okay, similarly, if you are using some ringing volume which is high, probably there should be different ringtones for daytime as well as for nighttime. For nighttime, when you have a phone call, probably the system should uh, instead of ringing loud, probably there should be some options where you actually choose something like a mild ringtone with some other visual information like change in color or blinking LEDs like that. Now duration. The second rule for feedback design is like you need to consider the duration for which a feedback will last. Okay, so that will be depending upon your requirement. If it's an emergency signal feedback, probably it needs to be provided for a longer duration. Okay, it will be a continuous, probably a beep sound, because you want people to address that particular condition whenever they, as soon as possible. Okay, so that's why you do not want to stop giving that feedback. Similarly, if it is a battery battery low feedback, probably it will be a continuous feedback where people will show you feedback. But feedbacks like change in the status of pressure may be every few seconds or few minutes, because these are low priority feedbacks. So based on the priorities importance, you actually can have low priority feedbacks, medium priority, and then high priority. So high priority are those which are definitely you need to address because that may lead to risk, or that they have some other safety concerns. Next rule is intensity. Now you need to consider how bright, how fast, how loud particular feedback should be. Is it ambient or noticeable? Does the intensity grow in time or remain constant? So the change in the intensity also needs to be considered. Probably that will provide you contrast, and it will make a particular feedback or interaction different, feedback different to other. Repetition. Now how often you need to repeat. Okay, for example, your alarm go snooze for 5 minutes, then again it repeats after 5 minutes. Okay, so this is how you design feedbacks. So your mobile phone developer, he have designed by default the snoozing time is around 5 minutes, but you can also change that. Similarly, when it's an emergency, there is no repetition, it's a continuous signal. But when it is a signal like changing the status, okay, probably you will fix a particular time. For example, for every 3 seconds you will be showing the system level pressure. Again, the time, like how often the clock it's going to be changed, because this is a clock. Now it has a fixed time, second, minute, hour, all these are actually predefined scale. That's why you need to update your time every second. So it should actually follow that standard rule of hour, then minute, then second. However, for others there is no standard, so you can actually choose your own repetition time. Okay, so these are the rules how you can actually design feedbacks. Next is mode. Now, as I told you, modes are used when you have different uh, different modularity in terms of rules, functionality, as well as interactions. So you have mode 1, mode B. Here we have on and off mode, for example, on and off mode. So mode A will have different functional features, different interaction features, and different rules. Similarly, mode B have functions B, interactions B, and rules B. So this is required when actually you need to create meta rules in order to distinguish two different section of your algorithm. So that's why you use modes. Now there are two types of modes. One is called spring loaded mode, one is one off modes. Spring loaded are like those are active till the trigger is provided. That means it's like your shift key. Till you press the shift key, then only you will have that capital letter typing. The other type is like on off, one off mode, where actually you once you trigger that particular mode, it will remain at that particular state and it will end once you finish your action. So your caps lock button probably will be like that. In this particular case, we do not have the spring loaded modes. We have used both one off modes. That is, once it is start, it will start the therapy, and once it is stop, it will stop the therapy. So there is nothing that the user do not have to actually keep on pressing the start button to run that particular therapy. Okay. However, you can actually use these buttons instead of fixing their values. You can use those as spring loaded modes. For example, you can actually have a button like increase. So as long as you press this increase button, it will keep on increasing the pressure level. Similarly, you can have a button like decrease. So as long as you press this particular button, it will keep on decreasing the pressure value. So those are spring loaded modes. Now next is loops. Okay, so loops, as I told you, are the cycles, and they are actually defined to set certain durations, and those can be microsecond, millisecond, days, even years. Okay, so loops are about timing, determining the pace and overall lifespan of micro interaction. Okay. uh, so rules are, as I told you, like when you are actually sensing, okay, a particular sensor, for example. So how often you will be actually sensing that sensor. Okay. So you'll be looping continuously to read that sensor data every 3 seconds, and then you will be controlling every, this is third second, this is like every fourth second you change the current of the particular motor. Again, in from fifth, sixth, seventh second, you actually again measure the sensor value, and again you run this particular motor. So these are what are loops. Okay. Similarly, when you have multiple modes, for example, if you have mode A, probably a particular function, mode B, probably function C, this is function D. Now function D probably need 5 seconds to operate. Function C need only 2 seconds. So when you select a particular mode, that mode may run for 5 seconds depending upon the functional requirement of that particular mode. Similarly, if a mode B needs 2 seconds, it will enter that functional mode and then it will run for 2 seconds. So modes are also determinant of the timing for which a loop will run. Okay. Okay, so here are the ideas, actually the concepts, how actually you have come up with. So till here what we have discussed about like how you can make a concept which is more concrete in nature. Okay, so you have initially ideas, you used to have ideas, so which you use brainstorming and other techniques to generate a lot of ideas. You do different techniques of thinking, convergent, divergent, and then linear thinking. Then you actually selected few ideas and then you did a detailed micro interaction design. Now what we have are probably concepts. Now in the design process, which is the next phase of the development or the concept design process, where you need to select one or two suitable concepts to actually further prototyping or further manufacturing. Okay, now the process which is used for concept selection is again something scientific in nature, where systematically you compare various concepts like we did it for benchmarking as well as competitive analysis. We actually compare different concepts and then try to evaluate the concepts with each other and try to select the best concepts possible for our requirements or users requirement. So one of the concept analysis, so concept analysis is the process where actually we have certain concepts and then we screen those concepts using certain techniques and then we select particular concept. So this particular process is called concept analysis, and a very popular technique is what is called Puck's matrix. So Puck's matrix is basically a particular table, a matrix, which a technique which we use to select concepts. Okay, so let me give you an example of Puck's matrix. So a Puck matrix actually have set of criteria which are actually defined by the developers or based on requirements, user requirements, and these are the criteria against which we are actually evaluating our concepts. Okay, now these are the requirements which actually we had at the beginning when we were actually ideating. Now based on these requirements, now we are trying to evaluate the concepts. For example, here we have six concepts: concept 1, 2, 3, 4, 5, 6. So what we need in Bugs matrix is a product or a example which we considered a present solution or an equivalent solution for the particular problem. Okay, and we considered that particular concept or idea have all these value as 0. That means that is the standard, okay, which does not need increment as well as decrement. So all the values in terms of cost, we say okay, this is whatever it is, we do not have any option. This is like 0 means this is not bad, not good. Technical complexity, not bad, not good. Safety, not bad, not good. Ease of use, not bad, not good. Portability, these are like the various features I was talking about. Effectiveness, not good, not bad. So this can be a product which is a competitive to your concepts, or it can be a product which serve the requirements, may not be exact product like this concept, at least it is useful for serving those user requirements. So you will consider one of those and you will consider that as a standard product used for a particular problem, and then based on that you try to give plus or minus sign again your concepts. For example, cost compared to standard product, is your cost high or low? If you say low, okay, that means it is positive. If you say it is high, that means it is negative. That means cost wise this concept has a negative rating. Technically complexity wise this is less complex than standard product, that is it's a positive. Similarly, safety wise this is same as the standard concept. Similarly, ease of use wise it is same. Portability, it is more portable, that's why it is plus. Effectiveness plus. Then what you do, you count total positive 1, 2, 3. So 3 positive. How many same? 0, 0, 2 same. How many negative? 1 minus 1. So 3, 2, 5 minus 1, 4. So the score is 4. Similarly, for concept 2, you say cost is more than the standard product, that's why it's a negative attribute. Technically it is more complex, negative attribute. Safety wise it is better than the current solution. Ease of use wise better. Then portability wise it is better, and effectiveness it is better. Now total positive is 4, total negative same is 0, negative is 2. Again you have 2. Okay, you see now you have 4 versus 2. It's like this. Actually you have scores for all these various concepts, and once you have different scores, for example 3, 1, 5, 4, you try to rank them accordingly. So whichever is having the highest score will be like the rank 1, and the second score will be this one, third score will be this one, fourth, fifth. So this particular concept actually got the best score compared to others. So you will select this one, or you can also select the second best. So you can select top 2 concepts. So this the threshold you can determine whether you will be considering one concept or two concept. That it's up to you. But this is how you use Puck's matrix. Okay. The other way of concept analysis is weighted index method, where you compare the concept using similar criteria, but now you are providing certain weightage to your scores. So initially when you use Puck matrix, you actually count this individual plus or minus as equal as 1. So if 3 plus, that means it is 4. Oh, sorry, if there are 4 pluses, that means it is 4 score. And negative, you said it is again minus 2. That means each positive and each negative is counted as equal 1. But in weighted index method, certain positivity, certain negativity are counted differently. Okay. For example, when you provide a score, for example, across each of these costs, first you need to define a scale. For example, cost you will rate 1 to 5, technical complexity you will rate 1 to 5. So all of these criteria will have a scale 1 to 5, for example. Now for concept 1, when you are saying the cost, okay, now here in weightage index method, you do not need any standard product to compare with. You can use the concept itself to compare it. Now first you will provide a score for each of the concepts. So cost wise you will compare. So now you will compare horizontally here. So it is not like vertical like this. Here you compare concepts horizontally for cost, because now it's a comparison against cost. So cost of concept 1 probably it is more. So score is 2. Concept 2 cost is less, probably it is 4. And concept 3 is the best concept, best lowest price, that's why it is score is highest. So you actually compare across the criteria, and you compare horizontally all the concepts for a particular criteria. Similarly, technical complexity. Technical complexity, you say this is very easy, so you say 5. Similarly, concept 4 is medium, and concept 2 is very difficult, so 2. So likewise, you actually provide various comparative score for these concepts. Okay. Now you need to understand here, like in a weighted index method, you determine certain weightage for your concepts, and some of these weightage should be 1. That means cost is of 15% importance, technical complexity is of 5% interest, safety is 10% interest, then ease of use is 10% interest, portability is 20% interest, and effectiveness is 40. That means the scores that will be generated out of effectiveness will have highest weightage. Now what we'll do, you will multiply your ratings against the weightage. So 2 into 15.15, so it will be 0.3. 5 into 0.05, 0.25. So like that you will have 0.3, 0.4, 0.4. So you will have similar to that different scores here, which will be now weighted scores. Now these are weighted scores. Now when we'll add these, you will have certain values which will be again in the range of 0 to 1. So for example, you will have 0.9. Here you will have 0. Or may not be. Actually, these may not be in the range of, these may be varying also. It can be like uh, for example 4.9, this is 3.0, this is 6.0. So this is the highest score, so it will give you rank 1, and here you will providing rank second highest, rank 2, this is rank 3. So using weighted index method, this particular concept got the highest score, so you will probably select this concept for final prototyping or wireframing. Okay, so that's how you do concepts screening as well as analysis. Now once you have finalized your concepts, the next thing you do is wireframing. So wireframing, as you know, as we discussed previously in I think lecture week 2, lecture 3 videos, when we discuss about the 5 layers of thinking about a particular UX problem using Gerard model, we talked about the wireframing layer. So wireframing basically is the visual representation of the structure, how various elements will be positioned in the interface. So it will define the overall space and how you will be having different elements, how you will be positioning it. Okay. So the best practice of designing wireframe is that you start with hand sketches and then you digitize it. So once you have the wireframing, then only you can move to prototyping, which can be of any type. So wireframing allow you to determine where you will be positioning your graphics or your interaction elements or your trigger buttons, etc. So for example, in that particular device, if you try to consider the wireframing, probably this, you will have 4 buttons, 3 buttons or 4 buttons, then you will have one central part, and this is, so this is how the wireframing will look. Now later only you will go and detail out what will be inside this particular box. So this particular framing of individual layout for each of the elements as well as interaction trigger elements is actually what is determined during wireframe. So this is a rough no, estimation of various features and functionalities. And once you start doing, you are finalizing with your hand-drawn wireframes, then you digitize those into something more concrete. Next is prototyping. Now prototyping is again the next level where you actually try to see whether your solution is actually viable, whether your solution is feasible, and you try to actually also user test your solution. So for that you need some level of more concrete concepts which is tactile in nature. So you need something which you can show to the user or the stakeholder. So you can have two types of prototypes. One can be high fidelity, one can be low fidelity. So low fidelity prototypings are generally paper based prototypes, which are basically low cost version of the prototypes, which can be just a representation of a concept with hand drawn sketches. Okay, and probably those are useful among the design team to actually do some sort of role playing, because users may not know how to do role playing. So basically those can be useful for role playing and storyboarding. See how actually you can use those low fidelity prototypes and try to see whether those solve your the particular user problem or not. And next is high fidelity. So low fidelity prototype benefit is that it takes less time, it also consumes less resources as well as cost, So the first stage of prototyping should be low fidelity prototype. Then you move ahead with high fidelity prototypes, which is something which is close to the actual presentation of your concepts. So high fidelity prototypes actually can be used and to collect actual true human information, the data. So you can actually conduct usability study using high fidelity prototypes. And actually you can demonstrate the features and get feedback, and then further go ahead with production ready prototypes. So production ready prototypes are again high fidelity prototypes only. So prototyping can have alpha prototypes, then beta prototypes. So beta test prototypes are the production version of high fidelity. Alpha prototypes are the initial version of high fidelity prototypes. Okay. Okay, so that's done for today's class. So in this particular class, we discussed about how you further convert the ideas into concepts using the micro interactions by designing micro interactions, and how we deal with each of the four elements of micro interactions. And also we discussed about a case study of designing a medical device, and I tried to relate these concepts while designing that particular product. And then at the end I discussed about how we select concept using pug matrix or weighted index method. And once you have selected the final concept, then you go for wireframing and prototype. Okay, so that's it for today. So if you have any question, please feel free to ask. Okay, thank you.